Lesson 2.3 continues to talk about our polynomials. It's polynomial functions of a higher degree in modeling. So when we did 2.1, we focused on linears and quadratics, right? So where the degree was 1 or 2. Those were our focuses. 2.2, it was our power functions, our monomials. 2.3, it's higher degree. So basically the cubics, the quartics, the quintics maybe. Mostly the cubics and quartics, I feel like. So a polynomial is actually made up of a sum difference of individual monomial terms. We talked about that in the last 2 lessons. These terms are to be written in standard form. So standard form, descending degree, starting with the highest power going to the lowest power. And thus, the leading coefficient will be in front, and the constant term will be at the end. So if your highest power is out front, highest powered term has the leading coefficient in front of it, constant term at the end. Now, example 1. Describe how to transform the graph of an appropriate monomial function, so x to some n power, into the graph of the given function. Support your answer graphically and compute your y-intercept as a check. Now, so before we grab and automatically start graphing in the calculator, let's talk about the relationships here. Okay, what do you see? What do you see on example A where it's g of x equals 4 times x plus 1 to the third? Okay, it's cubed. And that cubed basically is saying, okay, you know what my basic graph here is? X to the third. So an x to the third graph is what we are doing stuff to. It's what we're transforming. Okay, so how are we going to transform this x to the third graph? We'll talk about what that even looks like in a bit, but. Okay, we're going to translate left 1, because a plus 1 in the parentheses is left or right opposite the sign. Okay. And the 4 out front says we're going to have a vertical stretch by a factor of 4. Sounds right? Okay. Now, I will say, and we should probably always do this, but when I write my descriptions, because the first thing it does say here is to describe. When I describe this, I'm going to say that we're doing this to the y equals x cubed graph. Okay, so we're going to translate it, and we're going to vertically stretch. I'm just going to put it right here. And then next to it, I'll do the graph. So we're going to translate the graph of y equals x cubed 1 unit left and vertically stretch by a factor of 4. Okay, so that's my description there. We're going to take the graph of y equals x cubed. We're going to go 1 unit left, and we're going to vertically stretch by a factor of 4. Now, okay, officially, all of you should be able to visualize what y equals x cubed looks like. And why do I say we should all know what it looks like?
Because we had to memorize them.
It's one of your 12, yes? Okay. Now, and at that, some of them you may be a little foggy on exactly what the graph looks like at this point, but y equals x cubed is one we've used a little bit over the years. Okay, more this year than other years, but you should know it. Can you visualize what the graph of y equals x cubed looks like?
I can.
Okay. It's that increasing squiggle. Kind of, it's going up at a diagonal, but kind of jogs there in the center. I don't know how else to describe it. Okay. And we need to, graph it. And we'll talk about the y-intercept as a check here in a moment. So I'm going to set up a graph. Got my x and y axis. I think I'm going to go 4 in each direction in terms of my tick marks there. Now, let's start with the basics. Before we do any transformations, what does y equals x cubed look like? What points does it go through? Okay, y equals x cubed would go through 0, 0. So you put a 0 in, you get a 0 out. Where else would it go through? 1, 1. Because if you put in 1, 1 to the third is 1. And where else does it go through?
Negative 4.
Okay, if you put in negative 1 to the third is negative 1. Now, this is where you have to be smart about it. It looks like a straight line. I just graphed those 3 points, doesn't it? But is it a straight line? No. And I'm going to kind of sketch it in here. This is not my final graph, right? This is our beginning graph, so to speak. That's what it looks like. And you can even make it a solid line if you want to and just make it lighter or whatever. But now we're going to take that graph. One thing we're going to do is we're going to move it where? One left. So instead of it going through 0, 0, it's going to go through negative 1, 0, right? If we get our negatives and orders right. Okay. Now, this other point, 1, 1, from that centering point goes right 1 up 1, yes? But what happens when we stretch by a factor of 4? We talked about that last week. How do we vertically stretch something? Okay, but I need a specific point here to make this skinnier. Not the x, the y. Because it's a vertical stretch, which values go vertical? The y values. So we're going to multiply the vertical values by 4. So this second point in relation to that centering point is 1 right, 1 up. So we're still going to go 1 right. Instead of going 1 up, what's 1 times 4? 4. So I'm going to go 1 right and 1, 2, 3, 4 up. Is that making sense with you? Okay. My other point from the center originally went left 1, down 1. It's still going to go the same horizontal distance, so it's still going to go left 1. What about down 1? Negative 1 times 4 is going to take me down 4. So left 1, down 4. So should be at negative 2, negative 4 approximately. Now, if you graph this, bear with me because I am horrible about making this happen and look decent on the BenQ. Oh my goodness. Okay. Purple is my final graph. Does that work kind of for you?
Good enough. That's right.
Okay. Now, you can always check your calculators, right? Okay. One other thing it did say to do, okay, because it said to graphically, and I want to talk about graphically, it says compute your y-intercept as a check. How do I find a y-intercept? What's our general rule of thumb to find a y-intercept? If you're given an equation, I'm not talking about, we can see where the y-intercept ended up, right? But if we're going to check it, how do we, here's our equation, how do you find a y-intercept with your equation?
Plug in x is 0.
Plug in x is 0, because where is a y-intercept? A y-intercept is on the y-axis. What do we know on a y-axis? X is always 0. So if you plug in, and I'm just going to squeeze it right in here, if you plug in 0, 4 times 0 plus 1 to the third. Well, 0 plus 1 is 1. 1 to the third is 1. 4 times 1 is 4. Did that happen to match up? Yeah. That happens to match up with the point that we already have there. So that's just kind of a check, kind of a reassurance there. Obviously, you see the shift of left 1. Does it look skinnier?
I see so.
Okay. Okay, a lot less curvy, and that's a good way to describe it. Obviously, graphing these on the calculator in comparison is your best bet. Okay, that will show it a lot better than what I can do by hand. But that will show you that, this vertical stretch, both of these graphs go on infinitely. So it's not that it's taller, but it appears skinnier, doesn't it? And so that it stretches that curve out in the center a little bit more. Makes it a little more vertical. Okay, that was red. I did not realize that was going to be red. Okay. B. H of x equals negative of x minus 2 to the fourth plus 5. Well, let's talk about the pieces that you see so we can describe this graph. Okay. X minus 2 says we're going to go right 2. Plus 5 at the end says we're going to go up 5.
And then it's across the x-axis.
The negative out front says we're going to reflect across the x-axis. And what is our original graph here was going to be my other question. This is an x to the fourth graph. Now, do we know what x to the fourth graph looks like?
I do know.
You do now. Okay, so x to the fourth is not one I necessarily expect you know. It's a good one to learn. And we're going to talk about it a lot in this lesson. Okay, now, so you guys are graphing these on your calculator, which is fine. Just see, don't graph the actual thing, just graph y equals x to the fourth. Okay, now, Kylie made the comment, so it's a parabola, or it's like a parabola, however she said it. Here's my recommendation. Now graph y equals x squared, because then you can see the comparison. How is y equals x squared different from y equals x to the fourth? And there is a slight difference.
X squared like that, fourth is like that.
Okay.
It's
Science.
skinnier.
Yeah. So, yeah, if you're looking at your calculator, I guess I could graph on the screen, but y equals x squared is more curved at the bottom, right?
Yeah.
Y equals x to the fourth is flatter at the bottom, but then goes up straighter vertically.
Always more in shape.
Yeah. So,
does that mean there's more than one
Yeah.
x
Books.
Well-
intersect?
what?
Does that mean there's more than one x intersect?
There actually is not. It still just intercepts at 0, 0.
Oh.
I know. I see what you're saying. It just gets much, much closer. Okay, so let me write this in words. Okay, let's see, I'm going to talk about the reflect first. We're going to reflect the graph of, and what was the graph we were talking about? Y equals x to the fourth across the x-axis and translate two units right and 5 units up. So if you didn't already graph it, I think most of you did, but there's a y equals x fourth. It does look very similar to a parabola. If I put a parabola on the same graph, just for comparison's sake, because that's the best way I can, there's a difference there, isn't it? Okay. I'm just going to do a zoom in, because I'll kind of show you the difference in the bases a little bit. Right there's y equals x to the fourth. Notice how it's so flat. And there's y equals x squared. Okay? So, just kind of an idea. And I will tell you, y equals x to the fourth. That's not the only version of y equals x to the fourth. We're going to get there, okay? And talk about other options of what an x to the fourth graph might look like if it has other terms in it. But a basic x to the fourth is just translated and reflected. Looks like that. Okay, we ready to try and graph this by hand?
May as well.
Let's see. I have to be able to do what? Go up 5. So it looks like I allowed room to go up 6, down 3, and left and right 5. So I made my okay. So I just counted with my tick marks up 6 on the y-axis, down 3, and I have left and right 5. Not that we have to have all of those, but my recommendation, especially with this one, can we put a few points of what the basic graph looks like?
That's it.
If it's y equals x to the fourth, well, think about this. Y equals x to the fourth. When you plug in 0, you get 0. When you plug in 1, what's 1 to the fourth? 1. When you plug in 2, okay, it's 16. Am I going to graph that one? No, I'm not going to graph that one. But that's what makes it go up so vertically so much quicker, right? What about negative 1? Not negative 1, but positive 1. When you plug in negative 1, a negative raised to an even power is going to be positive. So it kind of looks like a parabola, right? The difference is when we do this, it's going to go up steeper quicker. I don't know. Not perfect, but, you know, you saw it on the screen. You get the gist of it. Okay, so now we've got to do ours. You can do this just like we shift parabolas. Where are you taking the vertex? 2 right and 5 up. There's my new vertex, yes? Now, when I go to graph this, what has to change?
The direction it's going.
Yeah, instead of being right side up, it's going to flip upside down. And can we still use that over 1, up 1 thing, except over 1, down 1?
Yep.
Yeah. So we can still say, okay, I'm going to go over 1. In this case, it's down 1. I can go over 1 the other way and down 1. And can we connect those? Something like that? Officially, it did ask us to do our y-intercept as a check. I don't even have a y-intercept on my graph, do I? But where can you anticipate it's going to be? It's going to be now negative somewhere, yes? So let's check and see what it's supposed to be and see if it makes sense. How do I find my y-intercept again? Put in 0 for x. So the negative of 0 minus 2 to the fourth plus 5. 0 minus 2? Negative 2. Negative 2 to the fourth.
16.
Positive 16. But the negative out front says the opposite of positive 16, so negative 16. Negative 16 plus 5 is? Negative 11. Does that seem legitimate?
That's what the calculator said.
Okay, that's what the calculator said. Okay. And, you know, and that's the thing. You can check on the calculator. But if I'm just doing this by hand, I'm going to go with, okay, I didn't get that one, but think about it this way. The next dot, remember, after you go the dot that is over 1, up 1, in this case over 1, down 1, the next set of dots would have gone over to down 16, right? And we're already up 5. So if you're going down 16, that does put you at negative 11, doesn't it? So just, things to think about. Things to kind of all pull together. Okay, questions on these? Okay. So the question was, do we need our scientific or our graphing calculator today? I said, oh yeah, somewhere. Okay, here's one of the places. We need them several places, but here's one of the places we need them. Example 2. Ask us to graph the polynomial function, locate its extrema and zeros, and explain how it's related to the monomials from which it is built. Okay, this is not a graph that I expect you to know what it looks like. Now, if we, and I know some of you have already graphed this, but if you haven't, you can at least think open-mindedly with me for a moment. F of x equals x cubed plus x. What's the gist of this graph have to be? Okay, y equals x cubed, right? Which means it's going to start low, it's going to be increasing, and it's going to end high. Now, what happens in the middle? That's a whole nother story. So, did you guys graph it? If you haven't graphed it, graph it. And you'll have to graph it to be able to do some of this stuff. So this is what we have, x cubed plus x. This one plus x, yeah. I would go to a basic Zoom 6 graph to get you started. Okay, so now, and what am I going to suggest? Because I agree, it kind of looks the same, doesn't it? What am I going to suggest?
You graph x.
Could you graph y equals x cubed just for comparison's sake?
They're pretty close.
They're pretty close. Is there a slight difference though?
Yes.
Okay. That point through that area going through the origin with our x cubed plus x is a little bit more diagonal, isn't it? As opposed to a more horizontal of the basic one. Okay, so it did say graph, which we've done. And let's see, I am going to put a sketch in my notes. I'm just going to put it over here because I have lots of stuff to write out. And this me graphing here is because it said to graph it. So this is just kind of, if you don't write anything down, you can claim all day that you graphed it on your calculator, but I'm not beside you when you're doing homework, am I? So when it says to graph something, minimal expectation would be a sketch in your homework. Okay? If we put some values here, I guess this is kind of more by hand. You can tell by looking at the graph it goes through 0, 0. What does it go through when you put in 1? 1, 2? Because 1 cubed is 1 plus 1. So we go through 0, 0. We go through 1, 2. What about when you put in negative 1? Negative 1 to the third is negative 1. Plus another negative 1, which is going to put me at negative 2. Okay, that's what your graph looks like. Locate its extrema. Do you remember the vocabulary word extrema?
I was gonna say
Max and min. Okay, so that is a calculus, pre-calculus, calculus word you've got to stick in your head. And I know it's taking a while, but you start off with extreme, but that can take you there because the mins and maxes are the extremes, right? Okay, so when they ask for extrema, It's asking you about any mins and maxes. What do we have in the way of mins and maxes here? Okay. Do we have any mins and maxes?
It means negative.
Well, min and max is like a max is a high point on a certain portion of the graph. A minimum is a low point on a certain portion of the graph. Do we ever have, I mean, what's going on here in the middle? It just curves through, yes? Is there ever a spot where, I mean, here's what I really need to say is when you think minimum, you've got to see something like that on the graph happening. When we think maximum, we got to think something like that. Do we have anything like those?
No.
No. Okay. And when it goes up and down to infinity, that doesn't count because it's going up infinitely. A maximum or a minimum is a point where you can tell me a number value of how high or how low it goes.
So what about like local min?
Local,
Absolute high.
so local, like here, this is a local minimum because the rest of the graph goes lower than it. Okay? As opposed to,
That would be like
here. Here we go. Here's an absolute max. That graph will never go any higher, right?
Yeah.
Here's a local max. It's a high point, but the graph goes higher than it over there. Here's a local min, because it's a minimum at that piece of the graph, but the rest of the graph goes lower than in other spots. Does that help with some terminology? Clear up there? Because at this point, that was what, chapter 1, right?
Yeah.
So I kind of expect you to know that vocabulary, so let's clear it up. Okay, so this one, there were no extrema. That was the first thing we had to answer. Next thing, zeros. What are zeros? What? No.
X-intercepts.
X-intercepts. So we talk about zeros, we want to know, are there any X-intercepts?
Just zero.
Does my graph cross the X-axis?
Yep.
Yes, and this one is pretty obvious, right? We don't have to do any work for it. There is a 0, I'm going to say at X equals 0. Now, we had one other thing we had to do, yes? And this is explain how it's related to the monomials from which it's built. So what were the two pieces of the equation here? There's an x cubed and an x. Can you explain how this looks like x cubed? Is that the obvious piece? It pretty much almost looks identical to an x cubed graph, right? It has the general shape of an x cubed graph. Now, this is a little harder to understand for the first time through, but how does it look like y equals x? What is y equals x?
Straight line.
That straight line, yes? So let me throw on. This might be too much action. I might have to. And let me zoom in. I probably need to take that extra graph off, but. So red is y equals x cubed. If you look at the y equals x line that just went through, what's happening with that in my blue graph there, the y equals x cubed plus x?
It kind of follows that middle point. Like,
Yeah. And if I let me get the extra graph off of there.
makes it more straight.
Yeah.
In the middle.
If this is y equals x cubed plus x, what do you notice happens right there at the origin? It like overlaps it identically, doesn't it? And so the whole idea is, why did my graph get a little more vertical there and stretch out a little bit more? It's because of that y equals x part. Okay? That y equal x part is what makes the graph a little more vertical there around the origin. Okay, so let's see. Yeah. So what I'm going to write here when it says explain how it's related to monomials from which it's built, shape is much like y equals x cubed. Overall shape is much like y equals x cubed, but near the origin, the shape is more like y equals x. Okay? So that's the information I'm going to write here. Overall shape is like y equals x cubed. But near the origin, shape is more like y equals x. Okay. So, curiosity, what you guys are packing up. Have any of you guys graphed B on the calculator yet?
Yes.
Did some of you? Okay. So, if you graphed B on the calculator, don't say anything right now.
yeah.
If you haven't graphed B on the calculator, think with me. If we kind of anticipate this one. We have an x cubed, yes? So what's the overall shape going to look like? That increasing thing. Any guesses, thoughts about what negative x is going to do?
More across the x-axis.
Okay, because what is negative x? Instead of going this way, negative x goes that way. Yeah, makes it curvier is a good way to explain it. So we'll look at that tomorrow if you haven't, It's just interesting what one little sign difference, how it can change the graph.
I know that
Okay, we'll pick up tomorrow. Homework is not due. I'll let you know. I'll figure out where exactly the cutoffs are and where we're going to make it due. Okay?